In this video, we study about SIC XC. Okay, so Simplified Instructional Computer. Extra equipment. Okay, and all the features of SIC will be considered here in SIC XC also. So the features we have studied, there is memory, registers, data formats, all those things we'll be studying, those 7 features. In addition to some new addressing modes we'll be studying in SIC XC, and 2 different types of formatting features in instructions we'll be studying. Okay, so in this architecture we'll write, in this architecture we study what? Memory we study, registers, data formats, instruction formats, addressing modes, instruction sets, and the 7th one is input and output. Okay, so now we'll start with memory. Okay, so memory structure for SIC is as same as SIC XC. Okay, so here memory structure of SIC XC is same as SIC. However, we have the maximum limit is 2 power 20 bytes, which means 1 megabyte. Okay, so in a SIC we had 2 power 15 bytes, whereas in SIC XC we have 2 power 20 bytes. This would be the maximum memory available. Okay, and next one is registers. So here we'll have a base register, S, T register, F register and all. Okay, so base register is denoted by B. Okay, so its mnemonic value is B and the number defined is 3. Okay, used for addressing. And we have another 2 general working register would be S. Okay, S, and another one is T. This 2 register is a general working register. Okay, and next one is F, which means floating point accumulator. In SIC, this floating point accumulator or floating point data type instruction will not be supported. Whereas in a SIC XC, floating point accumulator, and in the data format we have floating point data type. So this will be supported by the SIC XC. Okay, we'll see here data format. The next one is, and again SIC XC provides same data format as SIC. So whatever the data format we used in SIC will be same here also. Okay, but in addition to we'll have 48-bit floating data type. Okay, so we'll have what? Additionally in SIC XC we have floating point data type, where in SIC it does not support. Okay, in additional we have floating point data type. So this would be 48-bit. Okay, And now we'll see the format of this. Okay, S for sign, and this is for exponent. Another one is fraction. Okay, so S is indicated by sign. Okay, 0 for positive and 1 for negative. Okay, and this exponent is interpreted as unsigned binary number. Okay, so unsigned binary number should be in the range between 0 to 2047. Okay, whereas this fraction is interpreted as a value between 0 and 1. Okay, value between 0 and 1. Okay, and the sign bit hold 1 bit, and this exponent hold 11, and the fraction bit hold 36. Okay, now 36, 47, 48. So this is the format of floating point data type. Okay, so now we'll see instruction formats. Okay, here we have 4 formats of instruction. Okay, 4 formats of instruction in SIC XC. Okay, the first format is format 1. It has 1 byte. The format would be opcode alone, and this opcode hold 1 byte. Okay, which means 8 bits. The example we can say is R sub return to subroutine. Okay, so when I say R sub, the opcode for R sub would be 4C. So how do we write here? We'll write like what? 4C. 4 is 0, 1, 0, 0. C, the value of C would be 1100. So now 4C. So this is the object code. Okay. And now we go for format 2 instruction. Okay. So this is 2 bytes. Okay. And here the format would be opcode. We'll have 2 registers here. Okay. Maximum of 2. You can have 1 register also. So when I say clear accumulator, accumulator is a register. So we can go for an example like what? Clear accumulator. Okay. Clear accumulator. Okay. And we can also give an example of compare. Okay, A comma S. So what does it do? Compare the contents of register A and S. Okay, and now opcode, this holds 8 bits, and register 4, register 2 is 4 bits. Totally we'll have 16 bits of data. Okay, 2 bytes. Okay, fine. Now we'll write this example for compare A comma S. How do we write here? So we go for compare. Compare opcode value could be, we'll see, compare A0. Okay, so the value of A is 1010. 0 would be 0000. So here we have totally 8 bits. So register 1, accumulator. So as I said, accumulator is 0. Okay, so where do we write that accumulator is 0? So in base, in SIC assembler, the accumulator is denoted by A and its value is 0. Okay, so we'll go for accumulator here 0. 0, 0, 0, 0. That is 1 register. R2. So yes, S value would be for 4. Okay, it is defined as 4. So here we will write 4. 0, 0, 0, 4. Okay. So 4 in the sense, so S value is 4 in the sense we have to write, 0, 1, 0, 0. Now it's correct. 0, 1, 0, 0. Okay. So now when you compare this, you will have A0, okay, 0, and this is 4. Now for this instruction, what would be the object code? A004. Okay. So this is the object code for the instruction compare A comma S. One more thing, when I said this register, B register, so this is indicated by a number 3 used for addressing, and this for S and T, no, S is denoted by 4 and this T is denoted by 5 and this F is denoted by 6. Okay, I'll write it here. Base register, its number is 3. S register, its number is 4, and the T register, its number is 5. These two are the general working register, and the F is floating point accumulator, it have 6. Okay, so that's how I have taken here for register S, the value is 4. So this will be converted into binary here 0 1 0 0. Okay, so when you combine 4 4 4 together, you will get A004. For this compare instruction A comma S in format 2, so we will get an object code A004. Okay, fine. We go for format 3. Format 3 instruction. Okay, so this is 3 bytes. Okay, so here we'll have opcode, okay, N, I, X, B, P, E and displacement. Okay. So this is the format 3 instruction. Okay, here N specifies indirect addressing mode. Okay, so this we also study in addressing mode. Okay, and this I specifies immediate. Okay, and X specify indexed, and these are all the two new relative addressing modes, base relative and program counter relative. Okay, so this is base relative. Once again we will study this in addressing modes concept. Program counter relative addressing mode. Okay, so these two for calculating the target address of an instruction. Okay, and this E would be the format of the instruction, which format the instruction is taken. Okay, so to identify the format of the instruction. And finally the displacement. Okay, so for example, when I say here load accumulator 3, okay, so here what does it do? Load 3 to accumulator A, right? Okay, this is the function. Now we have to write this one directly. The value accumulator is 3 is loaded to the accumulator. So we have to write the format for this. So how do we write the format? Here opcode. The first one is opcode. LDA. What is the mnemonic code for LDA? It is 00. So we will write here. Okay, so and one more thing, we have to see the number of bit it holds. Okay, so opcode holds 6 bits and N holds 1, I holds 1 and X holds 1 and B holds 1, P holds 1 and E holds 1, and this displacement holds 12 bits. Okay, so 6, 1, 1, all such things. Okay, and now we'll see an example for load accumulator 3. Okay, so we are loading value 3 to an accumulator A. Okay, so as we seen, the opcode value of LDA is 0 0. So we will write 0 0 0 0 4. Okay, and again 0, 0 alone we can write. Other rest of the 2 zeros will be eliminated because since it holds only 6 bits. Okay. And here N, I, X, B, P, E, and later we go for displacement. Okay. This is not a indirect addressing mode. So N is 0. Okay. This is a immediate addressing mode. How do we say this is a immediate addressing mode? When hash is a part of an instruction, we directly say that this instruction is an immediate addressing mode. So I is set to 1. Okay. And this is no, X is not a part of any instruction. So this is not an indexed addressing mode. So it will be set to 0. Okay. And we are not going to calculate any target address using this base relative or a program relative addressing. So here again we will put 0. What is the format of the instruction here? 3. Format 3 is the instruction. So E specifies format of the instruction. If the format is 3, it sets to 0. If the format is 4, it's set to 1. Okay. So here the format of the instruction is 3. So here we'll have 0. Okay. And then we have to write the displacement. Okay. So displacement we have to write it here. What is the displacement? Here the value 3 is taken and directly loaded into the accumulator. So the value 3 would be written here. Okay. How do we write? 0, 0, 1, 1. Okay. 0, 0, 0, 0. And again 4, 8. Okay. It holds 12 bits from 0, 0, 0, 0. Now 4, 8, 12. Okay. So the value would be 3. Okay. So here we have to combine it. 0, 0, 0, 0, 0. And this one will be combined with what? Here. From 0, 0, 0, 0, 1 is 1. Okay. And this one is combined. Okay. 4 digits we have to combine. And again here 0. And this is 0. And this is 0. And here we'll have 3. Therefore, LDA 3 have the object code 010003. Okay. So this is the object code for the instruction LDA 3. Okay. This is how we find it. Okay. If it is an indirect addressing mode, it's set to 1. Now this is not an indirect addressing mode. It is 0. We say that this is an immediate addressing mode. How? Hash is a part of an instruction. We say this is an immediate addressing mode. X is not a part of an instruction. So this is not an indexed addressing mode, 0. We are not going to calculate any target address. So base relative and program relative is set to 0. And here we are using the format 3 instruction. That's why we set to 0. If it is a format 4 instruction, E will be set to 1. And here the displacement. Here the value is directly added to the accumulator. And this value is taken as a displacement. And now we framed the object code for this instruction. Okay. Next one is format 4 instruction. Format 4 instruction. So this is 4 bytes. Okay. And in 3 we have 24 bits. 12 plus 6, 18, 19, 20, 21, 22, 23, 24. So this whole 24 bits. Okay. Here we have what? 32 bits. Okay, so the format, how do we draw format for this? Draw like, okay, opcode, again, N, I, X, B, P, E, and next is displacement address. Okay, so here opcode holds 6 bits. And here 1, 1, 1, 1, 1, 1. Okay. Each thing carries 1 bit. And here we'll have 20 bits. Okay. 20, 6, 7, 8, 9, 10, 11, 12. Means 32 bits. Okay. So we go for an instruction. Example. I say plus J sub. We'll take this instruction. Plus J sub RDREC. Okay, we'll take that. We'll find an object code for that. Plus J sub RDREC. Okay. Now we have to draw the format here. Okay, I'm not going to close. Later we'll close. Okay. So JSON. Okay. So how do we say this instruction is a format 4 instruction? If plus is a part of an instruction, immediately we can say this instruction is a format 4. Here we couldn't find any plus in the instruction since it is a format 3 instruction. So when you see there is any plus in the instruction, which means that format 4 instruction. Okay. And now, so JSUB, the value of JSUB, the opcode value of JSUB is 48. Okay. So we'll write 48. Okay. So value of 4 is what? 0, 1, 0, 0. Okay. 8 is 1, 0, 0, 0. This is 4. This is 8. Okay. Now we'll write the opcode 0, 1, 0, 0. Okay. 4, 8. 8 we have to write. See, it holds only 6 bits. So 1, 2, 3, 4. Only these two will be taken. Okay. 1, 0. That's it. 6 bits. Okay. And N. Okay. Here we can say this instruction is neither indirect nor immediate. Okay. So will be set to 1. It is neither indirect nor immediate only. Okay. And X. X is not a part of an instruction. We'll set to 0. And we are not going to calculate any base relative or program relative address. So 0, 0. And the format of the instruction is 4. So we set to 1. Okay. And finally we go for displacement. So RD, REC. So in an instruction, RD, REC, okay, plus JSUB, RD, REC will occurs in the label here, RD, REC, 1036. So in this location only the RD, REC appears. So we have to write RD, REC in the location 1036. So we have to write like that. Okay. So value of 6 would be 8. Okay. 0, 1, 1, 0. This is the value of 6. And the 3 would be 0, 0, 1, 1. Okay. 0, 0, 1, 1. Okay. And now again, so we have written 6, we have written 3, and we have to write 0. 0, 0, 0, 0. So we have written 0 also. And we have to write what? 1. So 1, 0, 0, 0. Okay. So add it here 4, 8, 12, 16. And we have to accommodate 4 bits also. For that we have to write 0, 0, 0, 0. And to make it 20. Okay. Till here we have written and hold 16 bits. To make it 20 bits, we have to add 0, 0 onto it and close this table. And now we have to find the object code. Okay. So we compare this one. This is 4. Okay. So we compare 1011 here. This would be B. Okay. And we compare this 0001. This is 1. And we compare this 0, 1, and again 0, and here again 3, and this is 6. Okay. Now the object code for JSUB RD REC would be what? 4B101036. We'll check here in the table. Okay. See the source statement plus JSUB RD REC. What's the value given here? The object code generated for this instruction is 4B 101036 101036. This is how we find the object code for each and every instructions. Okay. Now we'll see addressing modes. Okay. Addressing modes in SIC XC. Okay. So we have two new relative addressing modes. One is base relative addressing mode. The second one is program counter relative addressing mode. And the third one indexed addressing mode. And the fourth one, immediate addressing mode. And the fifth one, indirect addressing mode. Okay, now we'll see here base relative addressing mode. Okay, so these two addressing mode to calculate the target address. Okay, for base relative we calculate the target address would be content of base register plus the displacement. Okay. Okay, target address is equal to content of base register plus displacement, and it ranges 0 less than displacement which is less than 4095. Within this range it has to be. Okay, and for the program counter relative addressing mode, the target address would be program counter. Okay, either you can put like this or square bracket, whichever it is, plus displacement. Okay, and the range would be minus 2048 less than or equal to displacement within this range 47. Okay, so this is the range for calculating either base or program counter relative addressing. Okay, now this has to be noted, very important. Okay, so if X is a part of an instruction, okay, in an instruction if there is any X, it means that it is an indexed addressing mode. Okay, I'll write here, if X is a part of an instruction, okay, instruction, which means it is an indexed addressing mode. When X hash is a part of an instruction, okay, which is a part of an instruction, we say that it is an immediate addressing mode. Okay, so here for index you go for X. You have to check in an instruction if there is any X is a part. For immediate we have to check in an instruction if there is any hash symbol. Okay, like that. Likewise we have what? Act is a part of an instruction. We say that it is an indirect addressing mode. Act is a part of an instruction. We say that instruction is a indirect addressing mode. Okay, we will see an example how to calculate the target address using program counter relative addressing mode. Okay, so we'll see an example. We'll write a heading, program counter relative addressing mode. So here we'll take an instruction, we'll take this 10.0.0.0 first STL RET ADR. This instruction we'll take and we'll calculate using program counter relative addressing mode. So I'll write the instruction here, 10.0.0.0 first STL RET ADR. Okay, so listen carefully, and this 10 indicates the line number. Okay, which line the particular instruction appears, and the 000 indicates the location of the program. Okay, the starting location of the program, and first is a label, and this STL RET ADR would be the instruction. As we know that STL is an opcode. Okay, so now we have to find what type of an instruction this is, either format 3 or format 4. We couldn't find plus symbol in an instruction, so we find that this is a format 3 type instruction. So this is format 3 instruction. Okay, now we start. Okay, the instruction starts at the location 00. So format 3 instruction holds 3 bytes. So we have to move to the next location. Okay, that would be the address to be executed in the program counter. As we know that program counter holds, or we say the stores, the address of next instruction to be executed. So here the program starts at location 0000. So 0001, 0002 and 0003. Skip this 3 part and next location would be 0003. And this is a 3-byte instruction. If it is a 4-byte instruction, we have to take this also and we go for the next location. That would be 0004 maybe. Okay. Now this is a 3-byte instruction. We'll take this one. Okay. 0003. Now the program counter have 0003 value. Okay. Next, we have to find the target address. No. So what is the target address formula? We have to find the displacement using the program counter relative addressing mode. So here the target address formula would be content of program counter plus displacement. Okay. Here in this instruction we will be finding displacement. Okay. So we have program counter value. Now we have to find the target address value. So TA would be target address. Here the target address is what? Return ADR. Okay. Which means the label starts from which location. We have to find that. Okay. So RETADR. Here we will come across. See here. RETADR. The location here is 0030. So that would be your target address. 0030. Now we have to apply these two values in the formula here. So now the target address would be 0030 and the program counter would be 0003 plus displacement. Okay. Now 0030 minus 0003, which is equal to, we'll take this here, displacement. Okay. Now we'll go for hexadecimal subtraction. 0030 0003. Okay. So when we get a borrow from here, this would become 16 and here it would become 2. Okay. 16 minus 3 is 13. Now in hexadecimal value 13 is D. Okay. So we write D here and here 2 minus 0, 2 and 0 here. So the displacement would be, we found the value of displacement is equal to 002D. Okay. Now we have to draw the format for format 3 instruction. Okay. So we'll draw it here. Opcode we have N, I, X, B, P, E and displacement. Okay. So this is the format. Okay. So and this opcode holds 6 bits and this is 1 and it holds 1, 1, 1, 1 and the displacement holds 12 bits. Okay. Now we have to write opcode. So what is the opcode here? STL. The value of opcode is what? 14. Okay. So we have to write 14 here. So we'll write 14. So 14, the value of 14 is 1 is 0001. 4 would be 000100. This is. So we have to write 1, 4. 0001. For 1 we have written and for 4 is we have to take 01 alone because it only holds 6 bits. Okay. Now we can say this N and I. N is an indirect and I is an immediate. We could say this instruction is neither indirect nor immediate. So we have give 1, 1. X is not a part of an instruction, so it is set to 0. I haven't calculated this instruction using a base register, base relative addressing mode. So it is 0. So I have calculated this instruction using program counter relative addressing mode. So now it is set to 1. I have a format 3 instruction. Now E is set to 0. Now we have to fill the displacement values. What is the displacement value here? 002D. Okay. Totally it holds 16 bits, but we cannot accommodate the 16 bits here. As far as now the displacement holds 12 bits. So we have to write only 12 bits in the box given here. Okay. So D value, okay, 002D. D would be 1101 and 2 would be 0010 and rest of the things 0, 0, 0, 0, 4 plus 4, 8, 8 plus 4, 12. Okay. So and we have to eliminate this 0 here. We shouldn't write because it holds only 12 bits of displacement. Okay, so now we have to combine 4 bits together and we have to generate a object code. Here, combine this 4 bits, we will get 1. Okay, so 1, and this 4 bits 0 1 to 1 1, so we will get 7, and this 0 0 to 1 0, we will get 2 value, and this one is 0 0 0 1 0 is 2, and 1 1 0 1 is D. Okay, therefore we have 17202D. So this is the object code for the instruction STLRETADR. Okay, so we will see that here. See, so we have taken this instruction first, STLRETADR. The instruction is what? 17202D. Okay, so this is how we have to find the object code for each and every instructions. Okay. So now next we will see base relative addressing mode. Okay, so base relative addressing mode. So we'll take an instruction 1056 STX length. Okay, so and this is a format 3 instruction. There is no plus symbol, so it is a format 3 instruction. Now we draw the format 3 instruction format. Opcode N, I, X, B, P, E, displacement. Okay. So this is 12 bits and this is 6, 1, 1, 1, 1, 1, 1. Okay. Now we have to calculate target address, the content of base register and displacement. Okay, so as we know that this is an instruction and this would be the opcode. Okay, so the value of STX would be the value of STX is 10. So write it here, the value of STX 10. Now, so the target address calculation, we have to find the displacement. Okay, so here the target address length. Okay, so where do we find the length here? According to B register, base will contain the value of length, okay, during the execution of a program. The address of length will be considered during the execution of the program. That is the use of base register statement. Okay, so we will take this length target address would be 0033. Okay, now 0033 would be the target address. As I said earlier, base will always consider the address of the length. Again, now base would be what? 0033. So we call it as base is equal to length always. Okay, now plus displacement. These two holds the same address value. Therefore, displacement would be 0033 minus 0033, which is equal to 0000. That is the value of displacement. Now we will draw the format for this. Okay. So opcode STX, the value of STX is, we have seen 10. Yes, it is 10. Okay, so write the opcode 0001. Okay, and 00. Okay, so since it holds 6 bits, so this is the value. Okay, next N. We can say neither, this instruction is neither indirect nor immediate. Okay, so it is set to 1 and I is set to 1. Okay, X is not a part of an instruction, so it is set to 0. I have calculated using base relative, it is set to 1. Okay, so program counter is now 0. The format of the instruction is 0 because the instruction format is 3. Now we have to write the displacement. What is the displacement here? 0, 0. Okay, so the displacement value holds 12 bits. So accordingly we have to write. Okay, so as all it is 0, 0, 0, 0, 0, 0, 0, 0, 4, 8, 0, 0, 0, 12. Okay, so now we have to combine 4 digits to form a object code. Okay, so combine this 1, and when you combine 0, 0, 1, 1 is 3. When you combine 0, 0, 1, 0 would be 4, and this is 0, 0, and this one also 0. Therefore, we have got a value 13470000, and this is the object code generated by the assembler. Okay, object code generated by the assembler for an instruction what? STX length. Okay. Now next we see an example for immediate addressing mode. Okay, we see all types of examples in this addressing mode. Okay, so immediate addressing mode, we have an instruction. We'll take load accumulator 9. Okay, so the opcode would be, the format would be opcode. Again we write N, I, X, B, P, E, displacement. Okay, now this is a format 3 instruction. Okay, write the opcode value. LDA is 00. The value of LDA is 00. I think. Let me check. We'll check here. LDA 00. Okay, so we'll write opcode value. So holds 6 bits. You have to write accordingly. So 4, 6. Okay, and now we should say that this is a indexed, immediate addressing mode. So this is not an indirect. We set to 0. It is a immediate addressing mode. When hash is a part of an instruction, we say that it is an immediate addressing mode. Now X is not a part of an instruction, 0. Okay, so we are not going to calculate any addressing. Directly we are loading the value 9 to an accumulator. So these two relative addressing mode will be set to 0, and this is a format 3 instruction, so E is set to 0 because there is no plus symbol we found in an instruction. Okay, now the displacement would be what? Value of 9, you have to write it here. Okay, so how do we write to accommodate 12 bits? Okay, the value of 9 is 1001, and again we will write 00000. Okay, to fulfill the 12 bits. Okay, and now we have to find the object code, and we take this 0, combine this 4, 1, and again combine this 0, combine this 0, 0, and 9. So therefore load accumulator, okay, equal to 9. For this the object code would be 010009. Okay, this is the object code generated by the assembler. Okay, so far we have seen indexed addressing mode and base relative addressing mode here, and program counter relative addressing mode. Next we will see two of them are there, indexed addressing mode and indirect addressing mode. So next example would be indexed addressing mode. Indexed addressing mode. Okay, so we'll take instruction like stch buffer comma x. Okay, so now stch buffer comma x. X is a part of an instruction, so we directly say that the instruction is a indexed addressing mode. Okay, so how do we calculate this? And this is a format 3 instruction. Okay, so we calculate this using a base relative addressing mode. Okay, plus displacement. Okay, so the target address would be, we found it from the buffer. So we have to get it, the source statement with line location here. And what is stch buffer comma x, where it is stch. Here, so stch buffer comma x. So the target address of buffer would be from, and here 0036. Okay, so we have to write target address of buffer is 0036. And now base register. As I said earlier, according to this base register statement, the value of base would be taken from the length during the execution of the program. So the address of length would be here 0033. That will be calculated for base here 0033. As always, base is equal to length. These two will have the same address. Okay, so here displacement. Now calculate the displacement. Therefore displacement is equal to 0036 minus 0033, which is equal to 0003. This is the displacement. Now we have to draw the format 3 instruction. Okay, so initially we will have opcode. So stch is the opcode. The value of stch would be 54. Okay, so we'll write 54. 5 will be written as 0101. Yes, and 54 no. So 4 would be written as 01. The 00 will not be taken as it holds 6 bits. Okay, so 5 and 4. Okay, we have written. And next one is, this is opcode. Next one, N and I. Okay, so this is neither indirect nor immediate. Okay, so we can say this neither indirect nor immediate. Okay, and x is a part of an instruction, so we set to 1, and we have calculated using base address. So base is equal to 1, program is equal to 0, and E, the format of the instruction is 0, because we are using here is 3-byte instruction, I mean format 3 instruction. And the displacement. So displacement we have to write like this. 0011 is 3, 0000. Okay, 4 plus 4, 8. Again 0000. So 8 plus 2, 12 bits. Okay, so that would be the displacement. We have to combine the 4 things together, 4 numbers together. Okay, 4 bits together. 5, and combine this 0, 1, 1, 1, which is equal to 7. 1, 1, 0 would be C, and this is 0, 0, and this is 3. Okay, so now the stch buffer comma x. Okay, for this instruction the object code generated by the assembler is 57C003. We'll check with the source statement along with the object code. stch buffer comma x. See, 57C003. Okay, so now we'll see indirect addressing mode. Okay, indirect addressing mode. Okay, so we'll take instruction here 002A J at RET ADR. When at is a part of an instruction, we say that this is an indirect addressing mode. Okay, so now we'll calculate this. Okay, PC, we'll calculate this using program counter relative addressing mode, PC plus displacement. Okay, now we have to find the target address value and the opcode value, and finally the program counter next address of the instruction to be fetched from this initial address. Okay, so here it holds, the instruction starts at 2A. So format 3 instruction, so we have to go to B, to C, skip all these things, and the next instruction would be what? 002A. Okay, sorry, 2D. Now we have to write program counter is 2D. Okay, 2D. As it is, like we are using the 3 byte instruction, move the each byte and go for 1 byte, 2 byte, 3 byte, and the fourth bit is to be taken by the program counter. Okay, and now target address of RET ADR would be RET ADR. That would be 00. You have to find, yes, it is here, RET ADR 0030. So we have to write 0030. Okay, 0030 plus displacement. Okay, now the displacement would be 0030 minus 002D. We have to find the hexadecimal. Okay, we have to find the another way, like what? 0030 002D. So 16, when you borrow it from here, you will get 16. 16 minus D, which means D is here 13. Okay, so 16 minus 13 is 3. Okay, 0, 0, 0. So that the displacement. Okay, so this is the displacement value. Now we have to draw the format here. Okay, this is a 3 byte instruction format. So you have to draw the format for that opcode. For the opcode value for J is 3C. Okay, so write here opcode, the value of J is 3C. So you have to write 0011. Okay, so 3 and the C value is 1100. So we will write 11 alone as it holds 6 bits. Okay, N and I. So all such things we have to write. Okay, so this is an indirect addressing mode. It is set to 1. This is not an immediate, so it is 0. X is not a part of an instruction 0. We have calculated using a program counter relative addressing mode. It is 1 and base is 0. Format 3 instructions, so it is 0. And rest of the thing is displacement. So we have to write the displacement like this. Okay, 0011 is for 3 and 0000 is 0 and again 0000 this 0 because it holds only 12 bits. Okay, we cannot write this 0 here. Now we have to combine the 4 bits together. Okay, now 0011 would be 3, 1110 is E. Okay, 0010 is 2 and this is 0, 0 and this would be 3. Now the object code would be 3E2003. Okay, the assembler generated an object code for instruction J at RET-ADR. Okay, so this is indirect addressing mode. So we have seen indirect addressing mode, immediate addressing mode, and indexed addressing mode, base relative addressing mode, and program counter relative addressing mode. Totally 5 addressing modes we have seen. And next we are going to see about instruction set. SIC provides all of the instructions that are available in the standard SIC. Okay, so in addition to this, we have instructions that to perform floating point arithmetic operations. Okay, so like what add F we say, and sub F, mul F, div F, because SIC XC support floating point instruction. Okay, that's why we go for add F, sub F, mul F, and div F. Okay, floating point. Okay, supports. In addition to this, we also have register move instruction, RMO, register to register move. Okay, move instruction. So this helps to include register to register arithmetic operation. We say that add R, sub R, mul R, div R. This is the register to register move instructions. Okay, and also besides we have SVC. SVC is nothing but supervisor call. So this instruction communicate with the operating system to handle the interrupt. Okay, so as we know that interrupt is a high priority call. So the supervisor call what? Communicate with operating system and to handle the interrupt. That's why we are using SVC in the instruction set. And finally, we go for input and output. Okay, so in SIC-XC, the input and output operation can be performed using channels. Okay, so SIC-XC using channels. Okay, whereas in SIC we use using device. Okay, we have DD, RD, WR. Okay, but here in extra equipment instructional computer we use channels. We transfer instructions, I mean the data. Okay, so the instructions are one is SIO, another one is TIO, another one is HIO. Okay, so this is to start the IO operation, test the channel, IO channel, and now halt the IO operation. Okay, so we have to initially test the IO channel. If it is free, you can start it and you can start the processing, and after completion of the processing you can go for halt IO operation. Okay, so this is all about input and output channels. So far we learned in SIC-XC we have seen the features as same as in the SIC standard model. Okay, so registers we studied, and here we use 2 power 20 bytes, which is equivalent to 1 megabyte memory. The maximum limit of the memory in SIC-XC is 1 megabyte. And we have studied registers. Okay, so base register, S&T general working register, and F is a floating point register. Data formats we have seen floating point data type. Okay, so in SIC this data type does not support. Okay, and in instruction format we have seen 4 types of instruction, 4 formats of instruction, and addressing modes we have seen 5 types of addressing mode. Each one is explained with an example, and also we have seen instruction set, and finally we have seen input and output channels in SIC-XC.